Hi students, this is the section Binomial Distribution from the chapter Discrete Probability Distributions. The objectives for this section are for you to be able to determine whether a random variable is binomial, for you to construct or find the probability distribution of a binomial random variable, compute a binomial probability, and be able to compute the mean, variance, and standard deviation of a binomial random variable. Let's first define the conditions for identifying a binomial random variable or the conditions for a binomial distribution. If these four conditions are not met, the first four, those are the ones that we check. If these four conditions are not met, then we do not have a binomial distribution. A binomial distribution has to have a fixed number of trials. And in this case, we're going to refer to each of the times we conduct an experiment as a trial. There are two possible outcomes for each trial. We have either success or failure. In this case, success does not necessarily represent something with something favorable or something desirable. It's just what we're looking for. The third condition is that the probability for each trial, the probability of success in each trial is exactly the same. The trials are all independent from each other. The outcome of one trial does not affect the outcome of any of the other trials. And we're going to use the letter X, or in this case, the random variable labeled X, to represent the number of successes that occur. As per our notation, we're going to use N to represent the number of trials. We're going to use P to represent the probability of success. And just by using the complement rule, the probability of failure will be 1 minus the probability of success, or 1 minus P. Note how, again, success does not necessarily mean a desirable outcome. It just means what we're looking for. So if the probability of, you getting hit by a car, it's the success probability is not what something desirable. It's just what we're looking for. It's just the probability of what we are looking for. All right, let's practice determining whether a variable is binomial. A random variable is binomial. In this case, our instructions say for those that are binomial, for any of the cases that are binomial, we want to state the two possible outcomes, and we want to specify which one would be the success and state the values of N and P, which are the number of trials and the probability of the success. Let's determine which one of the following are binomial, starting with letter A. A fair coin is tossed 10 times. Let X be the number of times the coin lands on heads. We have to check the four conditions to decide whether this is a random variable that it's binomial. That there's a fixed number of trials, that there are two possible outcomes, success and failure, the probability of success in each trial is the same, and that the trials are independent. Is there a fixed number of trials? Yes, we're tossing the coin 10 times. Remember, the number of trials is not our sample space. It's just the number of times we conduct the experiment. So it meets our first condition. Second condition, there are two possible outcomes, success or failure. And we want to determine which one's a success and which one's a failure. If this is not well defined, then it would not be a binomial random variable. The number of times the coin lands on heads, which means we're looking for heads. Success will be heads. Failure will be, in this case, anything that is not heads, which would be tails. So it meets our second condition. Let me label them so we know which one's which. Our third condition is that the probability is the same in each trial. The probability when tossing a coin each time is 0.50, Our probability is 0.50 for heads and tails. In this case, it's the same. Number 4, this one's met as well, is the probability of the first coin landing on heads independent from the probability of the second coin and the third coin and the fourth coin. In other words, the outcome of the first coin affects any of the other outcomes of the other tossed coins. No. So, yes, it's independent and our fourth condition is met. Because all 4 conditions are met, then yes, it's a binomial random variable. If any of these is not met, then it would not be binomial. Second example, 5 basketball players each attempt a free throw. Let X be the number of free throws made. Is there a fixed number of trials? Yes, 5 basketball players. Our number of trials is 5. This condition is met. Second condition, do we have a well-defined success and failure event? Success will be the free throw made. Failure would be that anything else, so that they miss. We have a well-defined success and failure events. Now, condition number 3, is the probability the same for each trial? At this point, this is a matter of interpretation. If we're told, the example doesn't tell us, but let's suppose we're being told that on average or from the population that these 5 basketball players were taking off, I don't know, the probability normally is, 50-50, 40-60. If you're given any hint of probability, or if there's already some data that allows you to find the probability using the formula what I want divided by what I can get, then there's a well-defined probability, and each time a basketball player throws the ball, then the probability would be the same for each. But if we assume that each of the basketball players have different skills, then we can say that the probability will vary every single time. So it's a matter of interpretation. But for the sake of this example, let's say that the probability varies depending on the player's skills. Again, this is a matter of interpretation. So this one, I'm going to put that it's not met. But if we were given more information, we could say that it would be met. We already know that it's not binomial, but let's check number 4 just for practice. Are each of the events independent? Are each of the trials independent from each other? The fact that the first player made or not the free throw affect the second player? No. So yes, it's independent. The last condition is met. But due to the third condition being not met, this is not a binomial random variable. It's not binomial. Our last example, 10 cards are in a box, 5 are red and 5 are green. 3 of the cards are drawn at random without replacement. Notice our keyword, without replacement. Let X be the number of red cards drawn. Let's check our information. Is there a fixed number of trials? There's 10 cards in the box, true, but that's our sample space. 3 of the cards are drawn at random. That is the number of times the experiment is conducted. Second condition, is there a very well-defined success and failure cases. Let X be the number of red cards drawn. So a red card would be success. A not red card, in this case a green card, would be failure. What about our third condition? Is the probability for each trial the same? Because we're being set without replacement, that means that every single time I draw a card, I'm affecting the probability for the other cards. After the first time I conduct the experiment, after the first trial, when I draw the first card, because I don't put it back, I change the total number of cards I have, which means what I can get varies, and my probability will vary in each trial. Because the probability varies, then this condition is not met. Oh, the first two are met. And then our fourth condition. Are the events independent from each other? No, they're not independent. Because every single time I'm drawing a card, the number of cards are affecting, the number of cards left affect the next probabilities and also affect the following outcomes. If I draw 3 cards that are all green, that's affecting my coming events. Now I have a greater chance of getting a red because the first cards were green. I'm sorry. So the fourth condition is also not met. Then it's not binomial. All right. This is how we identify whether a random variable is binomial or not binomial. Let's now go over our probability formula that we're going to be using for binomial random variables. Let's suppose we have a binomial random variable that we label X, and it represents the number of successes in n trials. N trials in this case will be how many times we conduct the experiment, with success probability P is the probability of success, then the probability of obtaining a certain number of successes, X, is the probability of X equals the n combination X times the probability of success raised to the power of X times 1 minus the probability of success raised to the power of n minus X. We're going to just substitute the values in our formula. If you notice, the first option tells me how many possible combinations I can get, how many different possible combinations I can get using the different number of trials. The second term that we're multiplying is our probability of success raised to the power of the number of successes that I'm looking for. And the last component that I'm multiplying is the probability of failure raised to the power of the remaining of the number of successes out of the number of the trials made. I know it looks very fancy, but in the application way, and especially using the calculator, this gets a little bit more simple. You have to only worry about understanding what you're being asked for in order to be able to set your information appropriately and be able to ask the calculator what you want. Let's start with our first example. The Pew Research recently reported that approximately 30% of internet users in the United States use the sharing website Pinterest. Suppose a simple random sample of 15 users is taken. Let's check if this is a binomial random variable. We're going to look for if our four conditions are met. Is this a fixed number of trials? We're conducting a sample of 15 internet users. Yes. Is there a well-defined success and failure cases? In this case, what will be considered a success? That those internet users used Pinterest. So the fact that they use Pinterest. The failure will be that they do not use Pinterest. I guess you could also be user, not user of Pinterest. Number 3, is there a well-defined probability? Yes, 0.30. Would it be the same probability for each time I randomly sample? Would it be the same probability for each of the users? Or would it vary depending on which users you have? Because we're not giving anything specific on any information on the users, we're going to say then no, it doesn't vary. The probability will be 30 for all of them. And just so you know, for practice and because we're going to need it later, what would be the complement of 30% or 0.30? 1 minus p, the probability of failure would be 0.70. And is this an independent or dependent event? The fact that one internet user actually uses Pinterest affects another user. Again, because this is a simple random sample, I'm not assuming that they're friends or that they know each other or that they gave each other the reference of the website. So we're just going to say, yes, it's independent. The fact that one person uses Pinterest does not affect any of the other. Because all of these conditions are met, then this is a binomial random variable. Let's use the binomial probability distribution to find the probability that exactly 4 of the sample people used Pinterest. Our formula was the probability of whatever we're looking for was the combination x times p raised to the probability of x and so on. What we're looking for is exactly 4 of sample people using Pinterest. My number of successes will be 4. Let me change the color so it's more obvious where I got the information from. My number of trials, we have already decided what was the number of trials. It was 15. And my probability of success was 0.30. My probability of failure was 1 minus p, which was 0.70. I'm looking for the probability of x is equal to exactly 4. So after I substitute, this is what I'm going to be computing. 15 combination 4, and how many ways can I draw 4 people out of 15? Or how many different groups I can grab 4 out of 15? Times the probability of success, which is 0.30, raised to the power of number of successes I'm looking for, 4, times the probability of failure, which is 0.70, times the number of trials minus the number of successes. 15 minus 4, 11. This is what I'm going to compute. This is going to give you your answer. If I go to Desmos calculator, you have to, I went to Desmos and I opened scientific calculator. I go to function to find that NCR, that combination. I want out of 15 and how many ways I can group 4 times my probability of success, 0.30, raised to the power of 4, because I want 4 successes, times the probability of failure, which was 0.70, raised to the power of 15 minus 4, 11. 21.86 is my probability of getting exactly 4 people being users of Pinterest out of those 15.